Let's discuss equivalence of norms. So to prove that, so this equivalence of norms basically connects between different norms. Suppose we have an alpha norm and we have a beta norm, both are vector norms. How are these two norms connected? Okay, so to prove this, we have to first prove a theorem from real analysis. Then we can extend it to norms as well. So let's prove this first. Let f1 and f2 be two real valued functions. On Rn, not that this Rn n is finite. So this is for finite dimensional spaces. And suppose these properties has to hold for functions f1 and f2. The first property is similar to what we have as a non-negativity property of 1 and 1a of norms. So fi of x is greater than or equal to 0 for all x belonging to Rn, and fi of x equal to 0 if and only if x is equal to 0. So this is one property which has to hold. Next is similar to the homogeneity property which we have, which is f1 of alpha x is equal to modulus of alpha into fi of x for all alpha belonging to R and x belonging to Rn. Third property is not triangular inequality, but it is a continuity property. Fi of x is continuous on Rn. Okay. If all these properties are satisfied, then there exists positive constants C small m and C capital M such that the m times f1 of x is less than or equal to f2 of x is less than or equal to C capital M times f2 f1 of x. So f2 of x, if it satisfies all these properties, and if we are on a if they are real valued functions satisfying all these properties and x belongs to Rn, then we can actually jam this sandwich the function f2 of x between a positive quantity times lower limit and upper limit, which is Cm times f1 of x and Cm times capital Cm times capital C capital M times f1 of x. So how do we prove this? So for all x belonging to Rn. So let's look at the proof of this. So this also use few results from real analysis. So we'll define a function h of x such that h of x is equal to f2 of x divided by h1 of x for x belonging to S. And S is something which is known as a compact set. So H is set of all x belonging to Rn such that norm of x with respect to the L2 norm. Whether it could be any norm, is not really sure about it. So such sets are known as compact sets. Okay. The set of we can look at this something like a locus of all the points which lie on the unit circle. Okay. Then we know that there are few results which actually uh, follows from which how we've already defined functions f2 and sorry, here it is f1. how we've defined f1 and f2, h of x is not equal to 0 for any x belonging to x. Why? Why is this so? Because the x will only take values. Norm of x is always 1. Norm of x is 1. This value, f1 of x and f2 of x is, then norm of x is 1, it's non-zero, right? Then for non-zero cases, from 1 here, it is always positive. It's 0 only if and only if x is equal to 0. So it can never be, h of x will never be equal to 0 for any x which is belonging to this compact set. And also h of x is continuous on x belonging to s. This is because f of f1 of x is continuous, f2 of x is continuous, and the fraction f1 of x by f2 of x ratio will be a continuous function. So here we use something known as Weierstrass theorem, which is a result from real analysis. According to this theorem, if all these properties are satisfied, then H attains a finite positive max Cm and a finite positive minima smaller on the compact set. What does that mean? Cm is less than or equal to h of x less than or equal to C capital M. In fact, gives you Cm is less than or equal to f2 of x by f1 of x and equal to Cm. You can cross multiply this. Cm of f1 of x is less than or equal to f2 of x is less than or equal to C capital M times f1 of x. This is what follows from the Weierstrass theorem. In fact, the trivial case is actually from B. This is actually trivial, right? F1 of f2 of C, this is 0. Okay, what will x will belong to this compact set? So suppose we have vector z, and if we normalize it, then this is always this will always belong to the compact set for all 0 not equal to c belonging to R. Okay, and for z equal to 0, this result is trivial. So this function is actually, this is true for functions which satisfies these three conditions. In fact, this can be extended to norms as well, because norms satisfy these conditions. What about, yeah, norms satisfy these conditions. Are norms continuous? This is something which we can discuss later. Norms also seems to be continuous. So this can be extended to norms as well. F1 and F2 can be replaced by two corresponding norms. Okay. So I would write this as Cm times F an alpha norm of x is less than or equal to a beta norm of x into less than or equal to C capital M times alpha. So this is the equivalence between norms. So what is this? What is the consequence of this? So we have the norm of x, which is defined in with respect to one norm. Then we can always find positive quantities Cm and C capital M such that uh, any norm, any other norm can be bounded between these two values. Okay. So there's a corollary to this. Corollary. The corollary to this is if norm alpha and norm beta are vector norms, and sequence, and if sequence x of k, if it is a given sequence of vectors, then limit k tends to infinity x of k is equal to x with respect to alpha norm if and only if limit k tends to infinity x of k is equal to x with respect to the beta norm. So choice of the norms does not matter. Sequence always converges to the point x, whether it's alpha norm or beta norm. Okay, how do we prove this? Proof is simple. So we've already seen um, that Cm times x alpha is less than or equal to the norm of beta norm of x is less than or equal to, sorry, this is C small C capital M times alpha norm of x. This we already know, right? So let's look at, from this, we can also write Cm times the norm of xk minus x alpha is less than or equal to beta norm of xk minus x is less than or equal to Cm times the alpha norm of xk minus x. This one holds, okay? But we know with respect to alpha is tending to, so value is tending to 0. That is norm of xk minus x alpha, it is tending to 0, is tending to 0. As a consequence, this tends to 0 means this side and this side both are tending to 0. This is sandwiched between 0. So if the left side and right side of the inequality are tending to 0, then the middle value should always tend to 0. So norm of xk minus x beta should also tend to 0 as k tends to infinity. So it doesn't matter which norm you're using. Okay, let's stop this discussion here.